In Lecture 3, we looked at various point symmetry operations. We looked at things like mirror planes and rotation axes. But when we think about a discrete object, let's say a molecule, it could have more than one symmetry operation that would operate on it and leave the molecule unchanged. And so what we find is the symmetry of most objects contains multiple symmetry elements. What we're going to talk about in this lecture is how those elements go together in something called a point group. Now, some of you may have taken a class in group theory, and if so, you know that we could spend the entire semester talking about the properties of point groups. Here, we're just going to look at the most basic features of a point group. We're not going to do any linear algebra or matrix multiplication. But let's start by what is the definition of a point group. So in a mathematical sense, a point group is a set of operations. Our operations in this case are point symmetry elements. And that set meets the following requirements. First of all, the set of operations must contain the identity. So there must be one operation in the group that leaves the object entirely unchanged. This is not that interesting for us because everything has an identity, but mathematically we have to remember to include it. Another feature is that there would be a fixed point in the object for which every symmetry operation leaves that point unchanged, right? Hence the name point group. So what this tells us is that point groups can have the sorts of symmetry elements we talked about in Lecture 3, but will not have the travel symmetry operations like glide planes and screw axes. And then the last 2 points here are probably the most important. A point group must have closure. And what that means is that if I were to manipulate an object with 2 successive operations, the way that object looks after those operations must be the same as another operation in the group that could do that same thing in one step. And we're going to take a look at that in some of the examples that follow. And then finally, every operation in the group must have an inverse operation that takes the object back to the way it was before. And in some cases, we'll see that certain operations, like a mirror plane, might be its own inverse. So to kind of illustrate these aspects or properties of a point group, let's look at an example. We're going to look at point group 2 over M. Right? That's its name in the Hermann-Magwin symbolism. If you're still thinking in Schoenflies symmetry, it would be point group C2H. Now, the name 2 over M tells us that we have a twofold rotation axis and a mirror plane perpendicular to that rotation axis. So let's just take an object. Let's think of this like a molecule, if you will, and I've got this little hurricane-shaped thing here. But we're going to apply the different operations of the point group and see what operations must be present for it to be a valid group. All right, so we have to have the identity operation. Then let's go ahead and do the twofold rotation. Right? So rotate by 180 takes this point and puts it over here. Okay, the object is over here. Let's start with this first picture and then do the mirror plane perpendicular to the point. Right? This is the mirror plane we're showing here. And that's going to generate this object. Right? That's mirrored of the original object. And then because of the property of closure, if we were to do 2 operations in a row, we have to get a picture that we could get to in one operation. So let's imagine that we did the mirror plane first, and then we did a twofold rotation. That would create another object here. We would also get that same object if we did the twofold rotation first, followed by the mirror. So these 2 steps in either order will generate this object. Now, how do we go from here to here in one step? And the answer is that would be through an inversion, through the point where the twofold axis intersects the mirror plane. So there must be an inversion point at that place in the object. And that has to be there in order to fulfill the criterion of closure. Now, the other thing we might ask is, well, which elements are inverse elements of one another? Every symmetry operation in the group has to have an inverse that undoes the effect of that operation. So you can see that for a twofold rotation, the inverse would just be another twofold rotation. So the twofold rotation axis is its own inverse. For a mirror plane, same thing. If we operate by a mirror, we can get back to our original picture by operating with that mirror again. And then the same thing also holds for the inversion center. So these four symmetry operations make up a group. And that group is the point group 2 over m. You notice that in the name of the point group, we don't write the inversion center. We don't write the identity. We don't need to, because if you have a twofold rotation axis and a perpendicular mirror, through the steps I just showed, you can derive the fact that you must have an identity and also an inversion center. Sometimes we might speak of the order of a point group, which is the number of symmetry operations in a point group, and for this one the order would be 4. Okay, how many point groups do we have to consider? Well, for discrete objects, there's actually no limit to how many point groups there might be, because you can have rotation axes of any order. But in crystals, remember, we already determined that crystals can only have twofold, threefold, fourfold, or sixfold rotation axes. So we don't have to consider point groups that have any other kind of rotation axis. Because of that, in three-dimensional crystals, there are only 32 point groups that we're going to have to consider. We call these the crystallographic point groups. In this table, I've organized them in one way that you can think about these point groups. For me, the easiest thing is, first of all, to say, well, let's look for a rotation axis, and let's look for the highest order rotation axis we can find. So in the top row of the table, you see that we could have no rotation axis, right? That's a 1, rotate by 360. That's just the identity. If that's the case, it's going to tell us that we are going to have a triclinic crystal system. We could have just a twofold rotation axis. As it turns out, that would give us a monoclinic crystal system. We could have a threefold rotation axis. That would make the crystal system trigonal. We haven't encountered trigonal yet, but a trigonal crystal system is one where the highest order rotation axis is a threefold axis, and there's only threefold axes in one direction. We could have a fourfold rotation axis, that would be tetragonal, or a sixfold rotation axis, which would be hexagonal, or we could have one of these cubic point groups. And the thing that makes something a cubic point group is that you have intersecting threefold rotation axes that go along the body diagonals of a cube. And the lowest symmetry cubic point group is 2, 3. Let's generate the other point groups by doing different permutations on that idea. So in the second row, we see the kind of point groups that we might get if we have a roto-inversion axis instead of a proper rotation axis. Remember that a twofold roto-inversion axis is the same thing as a mirror plane. So this point group we call M. Then we could have a rotation axis and a perpendicular mirror plane, and that would give us the point groups we see in this row. And here we point out that there are some red entries in this table which are equivalent or the same point group. And remember, when we were talking about the roto-inversion axes, what did we say? We said a sixfold roto-inversion axis will do exactly the same thing as a threefold rotation axis with a perpendicular mirror. So 3 over m and 6 bar are the same thing. Right? So these two are not unique from one another. They're the same. And that point group is called 6 bar. We could take our original rotation axis, and then we could have twofold rotation axes that are perpendicular to it, and that gives us this set of point groups. In most of these cases, you get more than one twofold rotation axis that's going to be perpendicular to the main rotation axis, and those are generated by the same kind of thinking that we saw on the C2H example. That is, if you have one two-fold rotation axis perpendicular to a four-fold, you're always going to get another two-fold rotation axis that's at a right angle to the first one. We can add mirrors that are parallel to the main rotation axis, that would be this column, or mirrors that are parallel to the main rotoinversion axis, and that would be this row of the table. And finally, we could have a rotation axis with both perpendicular and parallel mirrors, and that gives us the bottom row here. We see a couple of other duplicates here. We see once again the 3 over MMM could be rewritten as 6 bar 2M. Once again, this is because of the equivalency of the 6-fold rotoinversion axis and a 3-fold rotation axis with a perpendicular mirror. And because a 2 bar rotoinversion axis is equivalent to a mirror, that's the reason why these are both MM2. So if we remove the duplicates, we'll see that there's 32 point groups here. We could organize them in a different way, and what we see is that each point group uniquely belongs to one and only one crystal system. If we don't have any rotation axes, then we're in the triclinic crystal system. If we have a two-fold rotation axis or a mirror plane, or a two-fold with a perpendicular mirror, that would be monoclinic. If we have perpendicular two-fold rotation axes or perpendicular mirror planes, then we're going to be in the orthorhombic system, these 3 point groups. Then if we have a 3-fold rotation axis, but not the kind we see in a cubic crystal, but all of the 3-fold axes being parallel to one another, we're in the trigonal crystal system. Then the hexagonal cells have the same kind of shape, right? And we saw that in 2 dimensions. We saw that those space groups that have either a 3-fold axis or a 6-fold axis or both, they all have the same shape, right? And that is seen also in 3 dimensions. Then we have the tetragonal crystal system with a 4-fold axis, and then finally the cubic crystal system where we have 3-fold axes and sometimes, but not always, 4-fold axes, but more than one 3-fold axes along the body diagonals of a cube. If you want to see the Schoenflies point group equivalent, that's contained in this table. I'm not going to dwell on this, but I'll just put this up there for your information. When we see an object, how do we go about determining its point group? So I'm going to walk you through one way that you might do that. So if we exclude the cubic groups, which are, their own thing really, and also the rotoinversion groups, we can do it in a kind of systematic way. We're first going to look for the highest order rotation axis, which could be 2-fold up to 6-fold. Then we'll ask, is there a perpendicular mirror plane? Then we can ask, are there parallel mirror planes? And then finally, if there are not parallel mirror planes, we might say, are there 2-fold axes that are perpendicular to the primary rotation axis? And there's a couple caveats here with the parallel mirror planes just to be aware of. Let's kind of walk through that in an example. So let's say that you look at an object, let's say a molecule, and you can see that there's a 4-fold rotation axis. All right, so that tells you right away, okay, it's got to be either one of the tetragonal point groups or one of the cubic point groups. If it's a cubic point group, we're also going to see these 3-fold axes. So let's say that there are not any 3-fold rotation axes. We just have the 4-fold rotation axis. Then we have basically these 5 possibilities. These are the tetragonal point groups. First question we're going to ask, is there a mirror plane perpendicular to the 4-fold axis? If the answer is yes, then we say, are there mirror planes that are parallel to the 4-fold axis? If the answer is yes, then the point group is 4 over MMM. If the answer is no, then the point group is just 4 over M. If we come back to the question about the perpendicular mirror and the answer is no, then we ask the same second question. Are there parallel mirror planes? If the answer is yes, then the point group is 4 mm. If the answer is no, we have one more question to ask. Are there twofold rotation axes that are perpendicular to the fourfold? And if the answer is yes, the point group is 4, 2, 2. And if the answer is no, the point group is just 4. Okay, so in this way, asking these questions, we can determine which of these 5 point groups we would have. Now, if you have a 4-bar rotoinversion axis, then you know you have different choices of point groups, and you can kind of go back to that table and then you start looking for mirrors. While we're talking about this point group 4, maybe this is another one where it would be interesting to look at the rules of the symmetry elements that must be in a group. So if we have point group 4, right, in Schoenflies notation that would be C4, what the name tells us is that we have a fourfold rotation axis. My question to you is, are there going to be any other symmetry elements in this point group? And if so, what are they going to be? Let's pause the video right now and think about that question, answer it, and then come back and we'll go over the answer. To answer this question, we have to think about the properties of a point group. So we, first of all, can start by saying we know there's a fourfold rotation axis. It has to have a direction. So let's say it's a clockwise fourfold rotation axis. And we know that must be there from the name, because that's the only symmetry element that's present in the name. We know that all groups must have the identity, so we at least are going to have an identity. Now you might think that, okay, those are the only 2 elements of this point group. However, we have to remember that the other properties, the property of inversion and the property of closure. Because the fourfold rotation axis must have a symmetry operation that is its inverse, that is basically that undoes everything that the fourfold rotation axis does, takes it back to the original position. The only thing that's going to do that would be a fourfold rotation axis that's counterclockwise. So we see that in this point group there are 2 fourfold axes. They're coincident, right on top of each other, one which goes clockwise and one that goes counterclockwise. And then because of the property of closure, if you think about it, if I rotate by fourfold once, and then I do it again, rotate by a fourfold axis twice, right? That's going to be 90 plus 90. That's a 180-degree rotation. Well, that's going to be the same thing as a twofold rotation axis. So that rotation axis in the molecule, we have 2 different fourfold rotation axes that go in opposite directions and a twofold rotation axis. So there are 4 symmetry operations in this point group, and its order is 4. Now, if you happen to have a cubic system, you notice that you have these intersecting threefold axes. Then we use a different logic to determine the point group. We're going to look and answer the question, do we have an inversion center? Do we have mirror planes? And do we have fourfold axes? And depending on your answers to these questions, that tells you which of the cubic point groups that you're going to have. Let's maybe do a couple of examples. So really familiar ones that we encounter all the time. If we think about a tetrahedron, all right, this is one way you might depict a tetrahedron. And if we ask the question, is there an inversion center? And you should be able to convince yourself that there is not an inversion center in a tetrahedron. If I were to invert this atom through the point, then I would end up over here and there's no atom here. You could say, are there mirror planes? And the answer is yes, there are mirror planes. Right? Those are going to bisect the cube along this, let's say, face diagonal, and there's going to be one that's going to bisect the cube along this face diagonal. And are there fourfold rotation axes? And the answer is no. There's no fourfold rotation axis in a tetrahedron. And so, from the answers of these questions, we can deduce that the point group must be 4 bar 3m. Okay, that's the point group of a tetrahedron. At the bottom here, we have an octahedron. We're going to ask the same questions. Is there an inversion center? Yes, there is. Are there mirror planes? There are a number of mirror planes. There's one mirror plane that would contain these 4 atoms. There's another mirror plane that would contain these 4 ligands. There's a diagonal mirror plane. So plenty of mirrors. And then are there 4-fold rotation axes? And I think that should also be obvious that along these axes, you want to think about it, the x, y, and z coordinates of the molecule, we have 4-fold rotation axes. So since the answer is yes to all 3 questions, the point group is M3 bar M. All right, let's finish the lecture by you having a go at identifying the point groups of a couple of different molecules or ions. So this one, dichlorobis-ethylene diamine cobalt 3. Here's the picture of it, right? We've got these chelating ethylene diamine ligands. What's the point group of this molecule? I want you to pause the video, go back to your notes, work through it, come up with an answer, and then come back and we'll go over the answer. All right, welcome back. Where do we start? We're going to start by looking for the highest order rotation axis. You should be able to see that, let's say, along this chlorine-cobalt-chlorine bond, there's a 2-fold rotation axis. All right, so we've got a 2-fold rotation, and that's the highest axis. I don't see any 3-fold or 4-fold or 6-fold rotation axes here. So that means our possibilities are just these 5 point groups. The next question we might ask is there a perpendicular mirror plane? And once again, you should be able to convince yourself that, okay, yeah, in the plane that contains the cobalt and the backbone of the ethylene diamine, there's going to be a mirror plane. And so if there's a perpendicular mirror, that means we've come down to either 2 over m or MMM. And then the question is, okay, are there any parallel mirror planes? And once again, here the answer is yes. Right? So there's one that bisects or contains both chlorides and the cobalt. There's another one that goes through the cobalt and then bisects the ethylene diamine molecule. And now we have uniquely identified the point group as being MMM. In Schoenflies notation, that would be D2H. And if we look at all the symmetry elements that are present, we didn't identify them along the way, but there's also 2-fold rotation axes that go through there. There's a 2-fold rotation axis that goes through here. So we have along X, Y, and Z directions, we have both 2-fold rotation axes and perpendicular mirrors. And then that also creates an inversion center, and I haven't written it here, but of course we have the identity. So did you get that one correct? Well, let's try another one. This one I think is pretty easy. Let's take a benzene molecule. So applying the rules that we had a couple slides back, what do you think is the point group of this molecule? We are going to start by looking for the highest order rotation axis, which pretty obviously is a 6-fold rotation axis here. So once we see there's a 6-fold rotation axis, we see that it could be 6 over m, 622, 6mm, or 6 over MMM. The next question is, what about a perpendicular mirror? Yeah, it's a flat molecule, right? So the 6-fold rotation axis goes right through the center of the molecule, and there's obviously a mirror plane perpendicular to it. So now we come down to 6 over m or 6 over MMM. And then the question is, well, what about the parallel mirrors? And the answer here is also yes. I mean, you can see there's a mirror plane that vertically, there's a mirror plane horizontally, there's a mirror plane that goes through here, mirror plane that goes through here. So there should be actually 6 mirror planes in this molecule. Here are the symmetry elements that are present as well as the identity. So did you get that one correct? I chose a couple of molecules that are pretty straightforward for this, but I would encourage you to seek out other examples and practice at trying to identify the point group symmetry of these different molecules. And then in the next lecture, we're going to take these point groups and combine them with the Bravais lattices to make space groups. And that's really the ultimate goal of how we're going to talk about the symmetry of crystals.